I guess we're gonna start again. So welcome back to IAP for for the last session of the morning, and we now have 4 contributed talks, and we'll start with Mario Morvan, who will tell us about an hybrid physics machine learning framework to model exoplanetary light curves. Well, the floor is yours. You have about 12 minutes, and I'll warn you at 3 and 1 on Slack.
Thank you very much. And thank you for inviting me to this conference as well. Let me speak here. So yes, we're going to talk of the potential use of machine learning and deep learning applied to transit light curves. So it's kind of a sub-part of what Ingo presented before, one of these observations we have for exoplanets. And the possibility, more precisely, of combining physics models, explicit physics models with machine learning models to solve our challenges. So it's going to be in 3 subparts. First, we're going to see what transit light curves are and just remind quickly the data and challenges that we're facing. Then discuss a model that we've been using to try and detrend and denoise transit light curves. And finally, see the possibility of combining with physics models. Okay, so typically, raw transit light curves can be decomposed into different components. That's just somehow arbitrary, but it could be divided into even more parts. But that would be on a first instance in between instrumental noise coming from our telescope, our detector, and then astrophysical noise from the source, possible various sources which are blended or companion stars, background, foreground. All this is included in noise that we want to disentangle from the signal, generally primary transits, but it can be secondary transits or phase curves. And so that's really a challenge here because we have noise which is often order of magnitudes more important than the signal that we're trying to detect. And just a reminder as well that most of the missions have been not only looking at individual light curves, but tens, hundreds, thousands, and tens of millions of light curves for the transit surveys. And even when we're looking at the future of characterization of exoplanets, as Ingo mentioned before, we're going towards surveys of characterization as well. So it really makes sense to think of global models to make use of the variety and the number of light curves and not focus anymore on individual detrending for the light curves. Yes. So here what we are interested in is the detrending of light curves, which is the general word that we're using in exoplanet sciences and in light curve processing, I guess. To denoise, simply to denoise, to remove the component from the instrument and the star that we're not interested in. It's really important both for detection and characterization. And most of the used techniques so far have been either local, performing well, but on single light curves, or linear or non-scalable to the hundreds of thousands or thousands even of light curves. So it makes sense to wonder if machine learning models, which are typically more scalable and really expressive and flexible in terms of their power, could be used here and help solve part or all of this problem. So now we're still wondering, so there's not yet any consensus yet on what method works best. That's the last thing to consider before trying anything. So our first attempt was to use a recurrent neural network to learn the noise structure in Spitzer light curve. So starting from a raw light curve in here, in which the transit signal is obvious, but also we have strong instrumental systematics, and we can see some jitter in here on this light curve. We trained a model to learn the noise structure and impute the signal during the transit by neglecting the transit, if you like, on the first instance. Then we remove this trend and it finished the pipeline by a classic transit model fitting, from which we extract the transit parameters. So here the pipeline is still in two steps, in classical, in this way that it is first denoising and then transit model fitting, but we replace the first part with a neural network. The architecture looks like this. So in input, we have the masked light curve along with covariate data, which in that case was centroid information, the movement of the target itself on the detector, which are imputed into a three LSTM layers network, which outputs two different values for each time step, the mean and the standard deviation, which parameterize the Gaussian likelihood, which is helpful if we want to have some idea of the uncertainty of and model the noise in output as well. And really the idea here that we are re-injecting, we're using this LSTM as a generative model to re-inject the predictions during the transit, and that's how we're predicting the noise during transit. So it works. No, it works well. It's still hard to say exactly how much better or worse it does compared to other methods, but it seemed to work quite well when we compared on some benchmark planets. But now it also makes sense to try and generalize this kind of approaches to larger data sets or to simulated data sets to be able to evaluate them more precisely and see their full interest. I think that the time series models are really powerful when it comes to many different light curves. And I'd like just to do a little parenthesis in terms of what the state of the art in terms of time series modeling, because here the idea would be to go toward a global, nonlinear, scalable detrending model, which would work for all the instruments. But is it something achievable now, or even in 10 years, or is it very, very far away? And just a little note that it seems that there's a sort of hegemony of deep learning in the fields of image processing and natural language processing, which is already a few years old. So there's already a few years of literature and very performant models, which are much better, far better. There's no discussion anymore than in classifying cats and dogs. We have to use ConvNet somehow. And for time series, it's a bit less clear. It really depends what the problem, how many time series we have. And for unsupervised and generative time series modeling, there are some models, but still it looks like it's lagging behind the other fields. And so it's positive, because it means that we're gonna have some progress in time series if we're optimistic modeling, and that this can be this is gonna trigger some progress again in turn for the detrending aspects in what we're interested in astronomy. So yes, the last study that I'd like to mention is the recent endeavor in which we wanted to use the transit model explicitly and combine it with our deep learning models. So for this, we really like a model which is differentiable, vectorizable, and also be able to use it on GPUs. And so in the end, we've just adapted an existing light curve forward modeling code in PyTorch, so that we can use it in a deep learning framework. And the first experiment that we did using this code was to try and solve the inverse problem, which is classically starting from clean light curves and trying to predict the transit parameters with a neural net. So we generated 2,000 synthetic transit light curves with random transit parameters and Gaussian noise. And we evaluated the model only on the prediction of one parameter, the most important that we're interested in, the ratio of radii between the planet and the star. We used the 1D CNN actually to compare different ones, but here the idea is really to compare different ways of learning rather than optimize the architecture. and so here we compared two different models with the same architecture. But on the first model, we're just simply training with a regression loss on the transit parameters. And on the second case, we are also using this regression loss, but we're also trying to reconstruct the input using the explicit transit model. Once we have predicted some parameters, we can reinject them in the transit model, and then add a reconstruction term in the loss, which is basically bearing the physical expert information that we have. We know that what the transit should look like, and if we do that, we observe an improvement in the test loss when we're using this additional physics term in the loss. So not only on the test set, but also if we're changing the parameter space, we see that this model generalizes better. So it's a sign that, in some cases, for some problems, it's really worth considering using the explicit model when we can. And also, yes, a good sign that this model works. And yeah, we should consider some hybrid models when we can, even if it's just a kind of a toy problem, this inverse problem. It pushes us towards trying to combine neural nets with this transit model. So that was just an example, but here there are different structures that we can consider, putting the neural network in input, in parallel, or in output of the transit model, and then train everything by propagation end to end. The last little thing I'd like to mention before wrapping up is that if we want to do everything end to end, then we're going to have to give up with lots of parameters, and the neural networks will have to give up exact Bayesian inference. But we can still consider using approximate Bayesian inference and for example, stochastic variational inference, for which some of the deep learning models can be optimized with as well, and which has some, we're not guaranteed to find the true posteriors, but still it is still very efficient and scalable and easier to combine with neural networks. So that's also a way of going forward using SVI. Okay, so just wrapping up, the neural nets are very flexible models, and I'm very optimistic toward the fact that not only they start to perform well, but in the future they have a bright future, which is slightly pending on the progress in time series generative modeling with deep learning. And for inference, a differentiable transit model combined with neural nets might help in some cases. And although we're losing the exact Bayesian inference, we're getting an end-to-end perspective, which is also really interesting. And so, yeah, we're going to continue to work on designing and testing this end-to-end hybrid models. Thank you very much.
Thank you. Okay, questions? I got one here.
Once you've removed all of the noise using the LSTMs, how confident are you in the science that you extract from the exoplanet transits? Because obviously these are very sensitive things, and you could be skewing your science if you don't dot your I's and cross your T's with this.
Yeah, no, absolutely, you're absolutely right, and you're touching the sensitive point here. That it's hard when we using real data on real planets to evaluate our model because we don't have the ground truth. We can only compare to existing literature, and in that case, the first study that we did, it was consistent with those observations. What we can say, but unless we're using simulated data, and we did some trials, and that's actually how we hyper optimized our models, on injected transits that we were confident in the prediction of our model. But otherwise, on real data, there's no way of being of even quantifying how well we're exactly performing. That's a real challenge, and we have to use simulated data if we want to ever quantify the level of certainty and confidence that we have.
Excellent. Thank you.
Any other questions from the room? We got none on Slack. Don't hesitate to send questions after the fact on Slack. I mean, speaker will look at them and try to answer them. I think we should move to the next talk. And first, thanks Mario again.
Thank you.
Thank you.